Hello students, today we are going to discuss Heisenberg uncertainty principle. So far in our course we studied modern physics, then we discussed wave function, and we also discussed the inadequacies of the old quantum theory. But for today class, Heisenberg uncertainty principle, now I have to give you a little recap of the course because it has been many days since we got connected and we interacted about the quantum mechanics. So it's very important that we do a little recap. Then further we will get in contact with this Heisenberg uncertainty principle. So in the last classes we focused on wave packet, and then during the study of wave packet we discussed that what kind of wave function we must use for a particle which has a certain momenta and a kind of certain position. So what kind of wave function would be associated with those kind of system? Like we can, in the quantum mechanics we cannot have a pure position state and we cannot have a pure momentum state. Both are ruled out by the quantum mechanics. Why both are ruled out by the quantum mechanics? Because if we have a pure position state, then the function, the wave function associated with which represents the wave properties would be a delta function, and if we have a delta function as a wave function, then the position is certainly known. There is no uncertainty in the position, but there will be maximum uncertainty in the momentum when we do the Fourier transformation of that. When we use the Fourier transformation, we discussed this in the last classes. So again, if I tell you a little bit of that, like for a pure position state, two things are ruled out in quantum mechanics. First one is pure position state. Pure position state, the wave function is something a delta function. And as we know by the properties of delta function, that delta function at a certain value, at x is equal to x naught or x is equal to 0, if x naught position is 0, then the value of the function is infinite at this position. So if the probability density del p by del x is tending towards infinite at a certain point, then we have to choose that point within those kind of dimension, and we cannot choose a particle at a certain locality having this kind of dimension where del p by del x, the probability density is tending towards infinite. So if del p by del x is infinite at a certain position, then the momentum, there will be maximum uncertainty in the momentum. If we do the Fourier transformation of this, then we will get the momentum, because we know the wave function in position space. Then to find out the wave function in momentum space, we need to do the Fourier transformation of this. Now Fourier transformation is kind of a bridge which transforms the one domain to another domain when both the domains are inversely related to each other, right? So phi k, we can find out the wave function in the momentum state by using this relation, this Fourier transformation, right? So when we use this delta function over here, we will find out that there are maximum and maximum uncertainty in the momentum, because we have a pure position state. Then we have more and more uncertainty in the momentum. We cannot determine the momentum. So, and the second case which is ruled out by the quantum mechanics is having a pure momentum state. So for example, if we have a pure momentum state, my wave function is a plane wave, and which is phi k e raised to power iota kx minus omega t. Okay, so here I have a wave function in which my wavelength of the system wave is, or the particle wavelength associated with the moving particle is 2 pi by lambda. Then lambda is equal to 2 pi by k. Now for a particular plane wave solution, now this is a plane wave solution. For this kind of solution, if this is our wave function, then there will be maximum uncertainty in the position. If we do the Fourier transformation again, I put the value of this, then in the momentum state I will get a certain result, right? So there are maximum uncertainty in the position when we have a plane wave function, and there is a maximum uncertainty in the momentum if I have a pure position state like delta function. So both of these are ruled out by the quantum mechanics. Then we did the ample discussion and made a vivid confirmation of the Gaussian function, that if we have a Gaussian function, then Gaussian function represents the best materialistic wave associated with the particle. Like, so what is a wave function? What kind of wave function we choose in terms of Gaussian function? Like a Gaussian function represents the supreme position of all these plane wave solutions. The plane wave solution is the most fundamental solution, so we have to choose this one, because the plane wave solution will give every possible answers we are looking for. So if I choose the plane wave solution here, and if I superimpose all different plane wave solutions, then within some kind of uncertainty in the momentum, I will get my wave function, and that wave function will be a Gaussian function. Like wave function, I can write this psi x is equal to phi k e raised to power iota kx minus omega t. Now this is a plane wave solution, but my phi k is a Gaussian function here, and if I represent my phi k with respect to k, my phi k is a Gaussian function, and this is the best representation, right? Now this is kind of Gaussian function. Phi k should be in this kind of form, minus k square by 2, something like this. Okay, so this is the representation of Gaussian function, and I told you that the maximum uncertainty is del k. And if I do the Fourier transformation of this, if I plug this into this equation, then by using the Fourier transformation, the wave function in the position space, my wave function in the position space, if I do the Fourier transformation of Gaussian function, now this is a Gaussian function. If I do the Fourier transformation of this Gaussian function, I will get a Gaussian function in the position space. Then my wave function in the position space would certainly be a Gaussian function. Obviously a Gaussian function, e raised to power minus x square by 2 with some another terms, some time domain terms. So this is, and if I find out the uncertainty product, then the uncertainty product is least here for when I use the Gaussian function. So that's why we choose the Gaussian function. So this was in all a total recap of the earlier classes, and we need to discuss that. So now let's move further, and today we are going to discuss Heisenberg uncertainty principle. Now according to this principle states that we can never simultaneously find out the exact position and exact velocity or momentum of the system in the microscopic domain. In the macroscopic domain, obviously classical mechanics explain you everything by those three equations, kinematic equations. But in the microscopically region or microscopic domain, we cannot find out both the position and momentum simultaneously with the complete precision. And this Heisenberg uncertainty principle was stated by German physicist Werner Heisenberg in 1927. So he particularly articulated the principle that if you try to find out more precisely the position of a particle, then the less and less precisely we can know the momentum, and vice versa as well. If we try to find out the momentum, then we cannot find out, there will be maximum uncertainty in the position, and this is uncertainty principle. So to find out the elementary results of this, we need to drive it out using superimposition again and using the wave packet. In the wave packet discussion, we superimposed two different waves having slightly different frequency and different wave number. We discussed that if I have two different waves, right? If I have two different waves, now I summarized this thing in the little recap. So I'm going to derive out the Heisenberg uncertainty principle from here on. So my first wave is a kind of representation plane wave, and second wave is also a representation of a plane wave. And if I superimpose both of these, then I will get a wave packet which is certainly moving with a constant with a group velocity, and the group velocity is the composite velocity of these two waves after the superimposition, right? So now the superimposition of those two waves is psi is equal to psi1 plus psi2, and mathematically you write here psi is equal to this. So if I use this identity, trigonometric identity, sin c plus sin d is equal to 2 sin c plus d by 2 into sin cos c minus d by 2. So my wave function opens out like this, 2a sin omega 1 plus omega 2, something like this. So you can we already discussed this thing. So the superimposition is psi is equal to this, 2a cos del omega by 2 t minus del k by 2 x into sin omega t minus kx. Okay, and we proposed this already, that omega 1 minus omega 2 is the kind of difference. So this is del omega, and this is a particular constant term. Now these if I choose many waves, more than two waves, many number of waves, then the difference in the frequency has some kind of uncertainties, del omega, and difference in all the wave numbers has some uncertainty kind of del k. So that's why we cannot take these things as constant. Now the summation is also a constant, always a constant. This is kind of mean taken over here. So I cannot take omega 1 minus omega 2 as a constant value. So this is a fluctuation, little fluctuation, which is del omega. Okay, so after the superimposition, I got two terms in the same equation. I got two terms, one is this one and second one is this one. Obviously this is the amplitude. So if I take the amplitude, then this is 2a cos del omega by 2t minus del k by 2x. Now the most important thing, if I focus on the last diagram, this is my diagram. Now this is the wave packet which is traveling in the x direction, and here I have the uncertainty in the particle location. Like I cannot locate between this position to this position. I cannot locate where my particle is. So I am taking the superimposition of two different quantum states over here, which is represented by two different waves. And if I take the superimposition of those quantum states, I can find out that exactly where is the maximum probability, where is the least probability, and within this range. Now this is my wave packet, and this is the amplitude representation. This whole representation by dotted lines is wave packet, and this wave packet, inside this wave packet, now this wave packet is also a representation of Gaussian packet, right? Now this is kind of a representation of Gaussian packet. That's why I told you to focus on Gaussian wave packet, right? So if I use this, now this wave packet is traveling with a group velocity vg. This wave packet is traveling with a group velocity vg, and there is an uncertainty in the position. If I choose two consecutive positions, x1 and x2, and if I plug these two consecutive positions over there, so the amplitude would be minimum at the nodes position. Now these are the nodes position, so on. So at the nodes position, my amplitude of the wave packet should always, now this is kind of superimposition as well. So you might have studied in the standing waves formation that at the nodes position the amplitude becomes 0. So these are the nodes position where my amplitude of the superimposition is 0. So I will use this condition over here, and this amplitude must be equal to 0 at the nodes position. So this thing must be equal to 0 at the node's position, and from here this comes out that cos function is 0, then this must satisfy the odd pi by 2, 3 pi by 2, 5 by 2, and 2n plus 1 pi by 2 terms. So this angle must satisfy these terms, right? So now this is the supreme position, and if I choose two consecutive nodes position x1 and x2, then I will get that this is equal to, for first node position, if I choose for first node position, then del omega by 2 t minus del k by 2 x1 first node position is equal to 2n plus 1 pi by 2. Now this node's position satisfy this angle, okay, and second node's position satisfy the next particular value, 2n plus 3 pi by 2. If I subtract this equation from this one, then I get this much, del k by 2 into del x is equal to pi. Now del x is the uncertainty in the position of the particle, and del x is equal to this much. I got from this relation del x is equal to this much, and I already know that k is equal to 2 pi by lambda, and k is equal to 2 pi by using de Broglie hypothesis, this is p by h, 2 pi p by h, or I can also write this as p by h cut, okay. K has a certain relation with that momentum has a certain relation with the wave number, and this relation is p is equal to h cut k. So del k is equal to this much, 2 pi by h into del p. Now if I plug this into the last equation, fourth equation I got, so del x is equal to h by del p, and this is del x into del px is the order of h. Now if we consider a group of large number of waves superimposing and with the continuously varying frequencies, so the result is something like this, or I can say is for the minimum bound I can write this is equal to h cut by 2. So I got my Heisenberg uncertainty principle as a elementary derivation. So now this is too much important for the understanding of quantum mechanics. Now I use the Gaussian representation to fix out this uncertainty principle. Now the Gaussian wave packet is some kind of wave packet in which we have the least bound uncertainty in the measurement of both position and momentum simultaneously. For the Gaussian packet, now this is actually what we got. Del x dot del px is equal to kind of h cut by 2. This is the least uncertainty we can get. Always the uncertainty product will always be greater than h cut by 2, but for the Gaussian function this is of the order of h cut by 2. So that's why the Gaussian function represents the best representation of the material particle, where if the particle is moving, then there is a wave